When you add a machine to an existing network, it needs to be configured to understand how to talk to other machines in this network. By talk, I really mean here TCP/IP protocol talk. If you want to send a frame, go ahead and do it. Send a broadcast, learn the MAC addresses, and just talk in frames, low-level frame communication. But most of our applications are built on TCP/IP, right? Telnet, web server, HTTP, gRPC, all of this stuff is built on TCP/IP. So if you need to go layer 3, layer 4 to play in that, you got to be configured. What do you need to be configured with? Well, you have to configure an IP address. You need to present yourself at that layer. Like, what is your IP address for that network? It's really hard to answer that question, right? Well, you can statically configure it as an admin. You know that this network is 10.0.0/24. That means I can pick any address from 10.0.0.0 until 10.0.0.0.255. That's not entirely true because some IPs are reserved for broadcast. So yeah, you can statically configure the IP. What else do you need? Well, you need a subnet mask, right? The mask is required for the machine to know what is the network that I'm in currently. Why do I need to know what's the network? You need to know the network because sending an IP packet to a machine within the network is different than sending an IP packet to a machine outside the network, right? And by that, I mean either it's a different subnet altogether or the internet, right? The former, if you send something within the network, all you need to do is just set the destination IP address as that machine, and the MAC address becomes that machine's MAC, and you can get that via ARP, address resolution protocol. But if the IP address is outside your subnet, then you have to, throw your hands up in the air and says, you know what? I have no idea how to communicate with this network. Hey, gateway, help me. So you would still make the destination IP that machine, but the MAC address becomes the gateway's MAC address, which is basically your router. Right? So that brings us to the third configuration, which is the gateway itself. What is your gateway? Right? What is this thing that I send it all my IP packets, right? All my frames, let's say, to be more specific, if the machine is not on my subnet. Well, so you need to configure the default gateway or the router. So that's the third configuration. And that becomes some nice to have op configuration. So these three are kind of required. I mean, you can go out without the default gateway and talk to each other, but the subnet mask and the IP is required. The default gateway, not really required if you don't want to talk to any other network outside of yourself. But if you do, then you have to have the default gateway, and then you have the optional one. And that's kind of a main topic of today's video, right? Is the DNS, right? What is my DNS server in case I want to talk to host names, right? I want to resolve domains back to IPs. What DNS server should I talk to? Which DNS server should I make this UDP request to? That's the DNS server. So you can statically configure that as well. You can put Google's 8888 or Cloudflare's 1111. Hey, you can spin up your own DNS server locally as in the same network or a different network and have that statically configured in the machine. Another one, what? Proxies. You can also configure a proxy so that, for example, all HTTP traffic always goes to this proxy. So there is a lot of configuration. So you can statically add all these configurations to your machine, right? But that's tedious, isn't it? Imagine like hooking up your laptop and then like connecting to the Wi-Fi and you have to put all these numbers in. Most users won't do that, right? Static configuration is still important, by the way. We need simplicity. the dynamic host configuration protocol, DHCP. So I want to dynamically configure my network. So in 1993, DHCP was officially released as a proposal, as an RFC, to solve this static configuration problem, to make it easier so that just I hook up and automatically have all this stuff configured. So what DHCP does is there will be a DHCP server, and most of the time this is your router. Your router plays like multiple roles, by the way, and one of the roles is the DHCP server. Yeah? And the DHCP server sits in the network, and they say, hey, it just listens. They say, hey, did anybody want an IP address? It leases IP addresses. And while it leases an IP address to the machine that requested, it says, hey, here's an IP address, right? And here's the gateway, and here's the subnet mask for this network. By the way, here's a DNS, right? Any request for DNS, talk to this guy, talk to this IP. Yeah? And here's a proxy. But how does exactly this work, this DHCP? So this is what I'm going to show in this video. I'm going to go through Wireshark, through the steps here, and talk through how DHCP actually works. All right, guys. So here I have beautiful Wireshark, and I just disconnected my Wi-Fi and I reconnected it again. And the reason I did that is because I want my machine to start fresh and send a DHCP request for the IP address. Right? So here's what I get after putting a filter. These are the 4 steps that we gotta get here. Right? So DHCP consists of 4 round trip. DHCP Discover, that's the client, this is me, says, hey, I want to find this DHCP server. Let me discover it, right? So this is sent to, if you think about it, DHCP is built on the UDP protocol, right? And because of built on the UDP protocol, it's built on the IP protocol. That means you have to put a destination IP and you have to put a source IP. Guess what? The destination IP, we don't know anything. When I first joined the network, I don't know anything. So what we do is we set the 255.255.255.255, which is a broadcast IP address. And the source, hey, guess what? I don't even know my IP address. So guess what? 0000. So that's the RFC. Says, hey, the destination has to be this and the source has to be this. So if we go to Wireshark, so this is the frame, layer 2, this is IP protocol, layer 3, right? And this is the layer 4, which is the user diagram. And this is thanks to Wireshark, actually parses the dynamic host configuration protocol and actually nicely parses everything for us for ease of read. So the first request is the discover. Let's go through the discover here. In the discover, right? Again, I'm sending just this, everybody gets this message. And whoever happened to be a DHCP server will actually reply. The rest should technically also drop it. So if I go to the frame layer, right? Let's take a look at this. So if I go to layer 2 here and take a look at the destination frame, the MAC address, look at this, FFFFFFFF. So even at layer 2, we really need to send it to everybody, right? And this is my MAC address, right, for this laptop, my machine MAC address, so that we get back the frame in case the server replies, right? So we need this to be correct. And in the IP layer, we notice that the destination is everybody. Hey, broadcast. The source is I don't have a IP address, so 0000. And then let's take a look at the dynamic host configuration protocol. I want to move to the most important one here. First of all, option 53. So what you notice, the DHCP is a bunch of options. It'll have this option 53, option 12, option 55, right? So option 53 is actually the message type, which is discover. This is me just sending a discovery message. Then going on, the second option, which is 55, parameter request list. You remember when I said that the server actually gives back all this configuration? Well, the client actually has to request this information. Okay? So if you notice, here is all the stuff the client actually requested. Subnet mask. Hey, DHCP or whoever's out there, I need the subnet mask. I need the classless static root. What is that? Is that the /24? I guess this isn't that the same thing as this? I suppose this is the same as this. Might be wrong. The router, the gateway, right? Who should I send my frames to in case I want to talk to someone outside my network? I need the domain name server, if you have one, so that all my DNS queries goes to that server. You might say, why don't we just hard code the domain name server? There are only few well-known resolvers, right? Let's just use those. The problem is, you can definitely use 8888 or 1111, right, as your domain. But the moment you do that, you will no longer be able to talk to local machines using their host names, right? I'm going to talk about that at the end of the video a little bit here, where if I have a machine is host name Hussein Mac 2, as we're going to say, and I have another machine called Hussein Mac, and then I have Hussein Ubuntu here, which is another server, right? I will not be able to ping the host names. Why? Because guess what? The host names need to be resolved, just like another DNS. And that DNS server is usually a local one. And guess what? It's mostly, almost always, the router as well. So there is a mini DNS server, the router host, and the router also hosts your DHCP server, and sometimes the router becomes also the proxy if there is a proxy configured. Yeah? So you can see that the router can become the bottleneck if it does all these jobs, right? So yeah, give me the domain name server so I can talk to my local peers. And we're going to talk about a little bit at the end of the video. Domain name, what is the postfix on my domain name? So if I join the network as Hussein Mac 2, what is the dot after that, right? Because guess what? When you join a domain name server, you gotta have a zone, and that zone gonna have a postfix, which is usually is dot local, or in my case .home.local. We're gonna see that. Right? I'm gonna skip that reserved, unsigned, DHCP. I'm gonna skip all of stuff. Hey, I request a private proxy auto discover. If there is a proxy, tell it to me. I love that to do out of C365 LDAP. Hey, if there is an LDAP given to me, if there is NetBIOS over TCP IP, this is an old stuff. I personally didn't use it. It's like before my time. All of this stuff before my time anyway. But yeah, I don't have much knowledge about the legacy aspect of NetBIOS, right? Maybe someone had that. But the size, I don't care about that. The client identifier, what's the client identifier? Usually the client identifier, it's like, tell me who are you so I can reply back. It's usually the MAC address, this is my MAC address in this case, right? And hey, I want an IP address for a specific lease time. IP addresses are usually not reserved forever, they are leased. And here the client's being greedy. They want they want the IP address for 90 days, right? And here's one of the most important options that I spent around a few days looking for this, right? Host name, Hussein Mac 2. So as a client, I am telling the DHCP server my host name. And this becomes very interesting for DNS later. This is the option that allows the DNS to know that Hussein Mac 2 is actually this IP address, so that anybody in the same network that happens to ping Hussein Mac 2 or want to query the DNS for Hussein Mac 2, they will use the same DNS server, which we requested right here, to actually ask that question. And that DNS will know because guess what? In the DHCP, they told us, the client told us its host name. And usually it's going to be Hussein Mac 2 by default, but it will be appended by the domain name, which is HusseinMac2.local or .home.local or whatever you set your DNS server to be. Right? So that's all the options. And of course, as I discussed in my backend engineering course, you need to really, because this is a message, you need to really specify where the message ends, right? As some sort of a termination. And this is basically where the message ends, right? On budget padding. So that was the first message. Guess what? Now we get a second message from 192.168 to 254 to 254, which is, guess, Guess who's this? This is my router. My router lives right there. The source is my router, and the message is called DHCP Offer. So my router is now offering an IP address to my machine. And the destination is actually, it sets the destination as this IP address, 192.168.255.144. Guess what? My machine doesn't really know that this is its IP address yet. So we just set it anyway. It's bogus at this point. Right? Why? Because this DHCP offer is just an offer, because we need to commit to this offer. So now this is the IP packets. Let's go to the offer message. How does the offer look like? So it's a reply. And look at this. The client IP address 00. Your client IP address is 192.168.254.144. So the server actually tells it, hey, by the way, here's a good choice. Why don't you pick this guy? And this is the offer for the client MAC address. The most important thing here is that we reply at the frame level by the destination MAC address, which is my machine. Because that at the MAC level, my machine will see that frame and it will go up in the layer and will discover that it's a DHCP offer message. And based on that, the DHCP client that is installed in my machine will discover that, oh, someone just made me an offer. Yummy. And basically, this is my MAC address of my router. So we're making an offer. Guess what? The DHCP server identify itself. It has to, right? Hey, by the way, I just replied to you, right? How does my machine receive it? Because it's destined for the frame at the layer 2 level. It's destined to it, right? Hey, client, this is your boss, DHCP server. This is my server, right? And here's a reply back. It's like, what if there are multiple DHCP server? I have no idea what will happen, to be honest. I'm pretty sure whoever authored the RFC designed it for all this conflict and rogue DHCP servers, but you can see what can happen, right? 2 DHCP servers can have absolutely reply, right? They don't know about each other, right? So this made me laugh when I first read it. So like, hey, IP address lease time. You remember what the client requested 90 days? You get 4 hours. You only get 4 hours. All right, and the rest of the stuff is interesting. Oh, yeah, of course, it's very interesting, the rest of stuff. Let's take a look at the rest of the stuff. And here's the subnet mask. Your subnet mask is 255.255.255.0, which is /24. That's what matters, right? Here's your router, which is the gateway. Of course, the DHCP server can absolutely be different than the router or the gateway, right? And in this case, the DHCP server is 254.254.254. The DNS is also 254.254. Right? I absolutely can configure all of this to be different machines, right? If I'm not lazy, right? I'll be spinning up my server and make this DNS and DHCP maybe, right? And when I did that, we also got back the domain name. Your home name is home.local. So I can literally use ping Hussein Mac 2, which is my host name, .home.local. This becomes like my local domain. Yeah? And this is a bunch of information. I have no idea what it is. Gateway manufacturer IDs and stuff like that, right? So it tells you all of that stuff. So this is what matters. The DNS, the router, the subnet mask. All right. So now we got the message. What does the client do? We're not finished with the handshake yet. DHCP, the client, the source, still doesn't trust. It says, hey, you know what? You're full of BS, DHCP. I don't trust you yet. So what I'm going to do, my source is still 000. So here at the client, it didn't trust that this is its IP address yet. Why? Because it needs to check if someone else might have gotten this IP while it receives this message, right? Because let's say there's a flood of machines plugged in all at the same time, right? Technically, you would think that DHCP should be atomic and serialize, right, these information and will never release 2 IP addresses at the same time, but sometimes it doesn't happen, right? That's basic database 101. kind of a situation, right? 000 is my source. The destination is still everybody. It's still talking to everybody. But I want to look at the frame level. Even at the frame, we're sending the frame as a broadcast. So still, I'm making an offer. I'm making a request. This is a DHCP request for everybody. Hey, by the way, guys, I want to request this IP address. What IP address, you might say? This is what I want to do. I want to request. Again, it's list all the parameter. It needs all of this stuff just in case. Just in case maybe something changed. I want all of this back. Tell me the subnet mask, the class of the route. And here's what I request. I am requested IP address 192.168.255.144. Can you guarantee that I'm going to get it? And here's, by the way, the last DHCP server that gave me this is actually this guy. Okay? And again, option 12, one of the most important thing here, in my opinion, is here's again my host name. Sorry, this is my host name, option 12. My host name is Hussein Mac 2. So just in case, if you want to update your DNS entries, that's me. Final thing, the server now replies back as a source to its IP address 254.144, and what it does is, I almost forgot to talk about the source port and the destination port. So the source port is always 67 and the destination is 68, and it flips in case of the client and the server because it's a UDP packet, right? The UDP must have ports, right? So I didn't talk about that, but hey, now the server now acknowledges that, hey, you got it. This is now you. Now, as per this message, the acknowledge message, that confirms the lease, confirms that this is you, and this confirms every single thing that we discussed. Here's again the domain name server. Here's the domain name. Here's all the information. Now the client can rest assured that this is, in fact, its IP address. Now that the client has an IP address, what the DHCP knows is now it knows that there is a new guy that just joined our network, 144, and their host name is what? Their Hussein Mac 2, right? Because we got it from the request. Now what the DHCP does, there is a relation between the DHCP server and the DNS server, and this is their relation. It's called RFC in 1997. Up until 1997, as far as I know, we couldn't dynamically talk to each other per host name. Why? Because if a machine just joined the network and you didn't really know how to talk to each other because you have no idea how to resolve host names, right? If machine 1 joins as Hussein Mac and machine 2 joins as Hussein Mac 2, and there is no DNS server that knows this information, then if you ping machine 1 from machine 2, you can't ping it. Why? Because you cannot even find the IP address. Sure, you can ping it using the IP address, but host name resolution will not work. So how do we make host name resolution work? Well, it's the job of the DHCP server, if you think about it. The DHCP server here does something called dynamic updates to the domain name server, right? Let's read the abstract of this. The domain name system was originally designed to support queries of statically configured database. That was the purpose. Here's a domain name. The name doesn't change. These are the domains. We change them infrequently, right? But sometimes we really need to change it. We need to make an update to it. While the data was expected to change, the frequency of this change was expected to be fairly low. And all updates were made as external edits to a zone master file. Right? Say, hey, someone just made the, hey, let's go ahead and update the DNS. You can absolutely do that, yeah? If you want to. Using this specification of the update opcode, it is possible to add or delete RR, I think stands for record set, right? Resource records, I think it was stand for, right? From a specific zone. Prerequisites are specified separately for update operation and can specify dependency. So if I look up DHCP here, right? Look at this. It is expected that in the absence of a secure DNS update, a server will only accept updates if they come from a source address that has been statically configured in the server description of a primary master zone, which is the DNS server. DHCP servers would likely would be likely candidate for inclusion. Oh, that's list. In the DNS server, you have to configure the IP address of the DHCP server, which is all has to be static. The DNS server has to be static. The DHCP server has to be static because it cannot dynamically configure the DHCP server. That would be a mess, right? So you would add the IP address of the DHCP server in the DNS server. Says, hey, if you receive an update from DHCP server, please accept it, right? So this way, if a DHCP server, which is, again, my router, talks to the DNS server, which is, again, my router, it's a local change, then go ahead and accept it. But if those are separate, they can actually talk to each other and make them update. So if you ever couldn't resolve a host name, that's probably why. The DHCP server couldn't update its DNS entry. I absolutely, when I first learned about this, you know, I had to dig deep for this information. Surprisingly, the internet is not spilling it out right, because I guess it's taken for granted. Yeah, maybe because it's just well known, right? But yeah, when 1997 happens, now you can do a dynamic updates and do all that stuff, right? And to end this video, there is a final concept that is called ZeroConf. And there's a whole book about it as well, discussing this zero configuration concept. Because technically, while DHCP and DNS does this job for us, it is still kind of configuration, if you think about it, because you have to set up this DHCP server, you have to do this DNS server. You might say, hey, just plug in the router and router does just job. What if you don't have a router, right? And you want machines in an IoT environment to talk to each other immediately? Well, that's where something called multicast DNS comes into the picture. I made a video about it a while back. In case I want to join a machine and I absolutely want to do zero configuration, I don't even want to do a DHCP thing, right? I don't have a DHCP server. These machines, if they are linked to each other, connecting like, I don't know, via a switch, they can still talk. If they support multicast DNS, which is like a mini DNS server in each one of them, they can find each other host name by broadcasting the message. Hey, I just joined the network. Who's out there? It's like, hey, okay, here's me, and here's, by the way, my IP address, and here's me, and here's my IP address, and here's me, and here's my IP address, right? So you can discover without an actual centralized DNS server, if you have mDNS configured in these machines, they can by default find each other this way. The host name, that is. And there's a service called Apple Bonjour, right? Which for the long, of Apple Bonjour. It's an open source, actually. Open source software that actually does that. I remember very back, I always thought this was a virus, like in the early 2000s when I first saw this. Like, what is this Bonjour thing? I never installed it in my machine. Kill. It was funny. So Bonjour is basically the mDNS implementation of things, right? And what if I don't have a DHCP server? Like, I don't even know. I don't have a DNS server. I can find them with mDNS, right? And the port, I think 55353, if I'm not mistaken, right? Yes, port 5353 is the mDNS port, right? But hey, I don't have an IP address. I don't have a DHCP server. Guess what? You can still communicate. Meet link local. This is the IP addresses. If you don't have a network and you still want to communicate with the networking, you can use this thing that if you ever seen 169.254/16, that's called the link local, which is, hey, I don't see anybody. I don't see any DHCP server. I'm not configured, so I'm going to assign myself a pre-assigned IP address. And anything start with 169.254 is reserved for this local communication. And the machine within the network, they will assign themselves these and going to make sure they are unique. So you can still talk with these IP addresses if you want. So that's another thing. So this is the goal of ZeroConf, where even if you can connect these machines together, right, and you can talk to each other with zero configuration. So that's a very long video to talk about DHCP, DNS, link local, and all that stuff. I hope you enjoy it. I'm gonna see you in the next one. Goodbye.